Okay, we're talking about radioactivity and radiation, and we need to say some things about the atomic nucleus. And here's a diagram. This shows a nucleus of an atom, or at least part of it, and you see it has neutrons and protons in it. And the question comes up, what holds the particles together in the nucleus? Why do they stick together in a clump? It seems that they ought to be pushed apart because these protons all have positive charge, and like charges repel. And the protons are very close together, so the force of them repelling each other should be very strong. So there's this force pushing the nucleus apart. What makes it hold together? Well, there's another force inside the nucleus, which we call the strong force, or sometimes called the strong nuclear force. And it's a force that shows up inside the nucleus of an atom, and that's what causes those particles to stick together. And it's one of four fundamental forces in the universe. And this is simply the way the universe is. There are four forces that we know about in the universe, and some of these we've already studied. Gravity is one of them, and we know that gravity attracts, is a force of attraction between masses. Any two masses pull together because of the force of gravity. Another force is the force of electromagnetism. And that's a combination of electrostatic and magnetic forces together. Physicists treat those mathematically as one force, even though it's often convenient to separate them into electrical forces and magnetic forces. It's one set of theories that describes the forces of electromagnetism. And then there are two other forces, what we call the strong nuclear force and the weak nuclear force. And the strong nuclear force and the weak nuclear force show up inside an atom, and they determine how things behave inside an atom. Just like gravity determines how things behave on a large scale, how the planets orbit the sun, they follow the laws of gravity. The strong nuclear force and the weak nuclear force, and also electromagnetism, determine how things take place, how processes occur inside an atom. And specifically, it's the strong force that holds these particles together despite the outward push of the electrostatic from positive charges repelling each other. And these four forces simply exist in the universe. We just say this is the way the universe is. Science doesn't really say why, but science studies what we see, what we observe. And when we study the universe and we study the particles in the universe, the atoms, these are the things we observe. We observe these four specific forces, which we can observe and describe mathematically. As far as why these forces exist, science doesn't say. And Newton faced that question too when talking about gravity, because he had described gravity very accurately with his equation for gravitation. And he said, as far as why gravity exists, I don't pretend to know. He would have simply said, that is the way God made the world, with these four forces. And scientists today don't question why these forces exist. That's more of a philosophical question, but they describe them. The theories of physics describe the universe that the scientists see and observe and study. Now let's look at a picture of a nucleus here. This is an atomic nucleus, and let's think about these forces acting. I've got the protons drawn there in a light blue and with a plus sign on them, and then the neutrons are the kind of tan color. And the protons are pushing away, so there's this outward force trying to push the nucleus apart, and that's the electrostatic force. That's the force of repulsion from the protons. At the same time, there's this inward pull, and that is a result of the strong force, or the strong nuclear force. And that force exists between protons and neutrons, and it holds the nucleus together. And those two forces are basically counteracting each other, and in most cases the strong force wins out and the nucleus is held together, and the nucleus is stable. But it turns out that large nuclei are unstable, and here's why. A large nucleus has more protons in it. So there's more electrostatic force. So in a large nucleus, this outward force gets really strong. The larger the size, the less effective the strong force is, and that's because the strong force has a really short range. It's a very, very short range force. If you move a far enough distance, you don't feel the strong force anymore. And from one side of the nucleus over to the other is enough distance for the strong force to weaken considerably, especially if it's a large nucleus. So if an atom has a nucleus that's really big, the particles over here aren't attracted as much to the particles over here by the strong force, because the distance is far enough away that the strong force is less effective because it's such a short range force. So because of that, the outward force from the protons repelling each other can be more significant than the strong force, and the nucleus can split apart. Some of these particles can pop off. And when that happens, we call that radioactive decay, and radiation is emitted and the element changes. If some of these protons leave, the atom has a different atomic number and it changes from one element to another. And this process is radioactive decay. And it occurs in these elements with large nuclei for that reason, because the large nucleus is too big for the strong force, which is very short range, to be very effective. So every element over element number 83 is radioactive. Every element above element number 83 has a nucleus that's big enough to spontaneously break apart.